first signal is delayed by some amount tau, so output x3 is also delayed by the same amount tau. Or if the second signal is delayed by some amount tau, then again the output is also delayed by the same amount tau. But if the first signal x1 of t is delayed by some amount tau1 and the second signal x2 of t is also delayed by some amount tau2, then the final outcome is delay is a addition of the first signal delay plus the second signal delay. So this output x3 of t is delayed by the amount of tau1 plus tau2. So this part we have discussed. Then the next property is the convolution with impulse signals that we have discussed. It is very useful property to identify the system response, because if we don't know the system response, then the input signal is considered as a unit impulse signal, and if any signal x of t is convoluted with the unit impulse signal, then we are getting the same signal back. So any signal convoluted with the impulse signal so is equivalent to the same signal as the output. So here we have discussed about with this property that we have even proved the property of a delay, that we have discussed if x of t is delayed by tau one amount and then convoluted with the delta of t, that is the output x of t delay with the tau one amount. And same here, x of t is convoluted with the impulse response unit impulse which is located at a tau 2 place is equivalent to the input x of t is delayed with the tau 2 amount. Then here we have discussed if the first signal x of t is delayed by tau 1 amount and the impulse delta of t is delayed by tau 2 amount, so output is x of t is delayed by the equal amount of tau 1 plus tau 2. That part we have discussed. The last property we have discussed is how convolution in a time domain reflected in a frequency domain. And for that you have a idea or conceptual the knowledge of the Fourier transform. But as the Fourier transform may be running in the next part by the Sony sir, yeah, we are not going to discuss in a detail, but here we just for a understanding point of view, we can understand the Fourier transformation first before we are using this convolution property for a Fourier transform. So we understand that there are two domains. One domain is a time domain in which the signal is represented as a function of time. So another domain is known as a frequency domain in which the signal are represented as a function of a frequency. So there are two domains are there, time domain and frequency domain. And for engineering point of view, especially electronics communication engineering point of view, we should have idea about the frequency spectrum, because this frequency spectrum reveals very useful property of the, like there is a bandwidth, the energy spectral density, power spectral density, and these properties are very useful for analyze the signal and to modify the signal, to change some property of the signal, etc. So if we can, so here if there is a pair of one signal x1 of t and its frequency domain version is x1 of f, and there is another time domain signal x2 of t and its frequency domain version is x2 of f. So we have a two pair over here. Pair 1 is the pair of time domain signal and frequency domain signal x1 of t and x1 of f, and consecutively the another pair is the time domain version of x2 of t and frequency domain version x2 of f. So if this is there, then we can say to convert the any signal which is in time domain to the frequency domain, we are using the Fourier transform. So Fourier transform is a mathematical tool to convert any time domain signal into the frequency domain signal. Assume x1 of t is a time domain signal. By taking the Fourier transform, we can produce a x1 of f, which is a frequency domain signal. The same way, x2 of t is a time domain signal, and if we take the Fourier transform of this one, then we are able to produce a frequency domain version of the signal as a x2 of f. So if this is the case, we have a pair of a time domain signal and frequency domain signal, x1 of t and x1 of f and x2 of t and x2 of f. Then if we apply the convolution operation in a time domain, then it is equivalent to the multiplication of a respective frequency domain version of the signal. So if x1 of t is convoluted with x2 of t in a time domain, it is equivalent to the multiplication of x1 of f and x2 of f, where x1 of f is the Fourier transform of x1 of t and x2 of f is the Fourier transform of the signal x2 of t. So here we can conclude that the time domain convolution operation in time domain is equivalent to the multiplication operation in a frequency domain. Then now it is a time to go with some example, right? There is a time to go with some example. So we can start with the first example. This example we have already solved in earlier lecture. So a few examples that we go very quickly, and we can give some exposure to some new example. And for new example, we spend some enough amount of the time. So the first very important part is if we have been given a two signal x1 of t and x2 of t. x1 of t is given as e raised to minus 2t into u of t, and x2 of t is given as e raised to minus 4t into u of t. U of t it represents the signal is basically starting from a 0. So you can if you plot this x1 of t with respect to time, right, and it is starting from 0 because it is multiplied with the u of t, and if any signal is multiplied with the u of t, so only positive part is appear as a output. So that's why the signal is it's e raised to minus 2t, so it is exponentially decreasing signal e raised to minus 2t, we can say. And if I plot the another signal x2 of t, so x2 of t is also exponentially decreasing signal, so we can say this is the time axis, it is x2 of t, and this signal is also exponentially decreasing with e raised to minus 4t, right? So these are the two signals, x e raised to minus 2t into u of t, and x2 of t is e raised to minus 4t into u of t, and here we need to find the convolution operation between these two signals. So let's choose the y of t is the output of this convolution operation, and the convolution operation is applied between the two signal x1 of t and x2 of t. So as per the formula, what the formula suggests, y of t is nothing else but it is the integration of the first signal which domain is tau multiply with the second signal which is represented as a t minus tau, and this integration is with respect to the tau. So this is the general formula to find the convolution operation between the two signal x1 of t and x2 of t. So first part is that we should know what is the x1 of tau and x2 of tau. So first we are representing this x1 of t as a x1 of tau, and this x2 of t is represented as x2 t minus tau. So this x1 of tau means every t, this t is replaced with the tau. So how the signal looks? This t is replaced with the tau. This t is again replaced with the tau. Becomes e raised to minus 2 tau into u of tau, right? This one is understand as a I use the different color, understand as a signal of x1 of tau, right? This is the signal of x1 of tau. And what about the second signal? So second signal is e raised to minus 4t into u of t. So e raised to minus 4t, but here it is t minus tau. So every t is replaced with the t minus tau. So this e raised to minus 4t becomes e raised to minus 4 t minus tau, and this u of t becomes u of t minus tau. So this is nothing else but this one is the signal x2 t minus tau. Okay, now as the limits are given from minus infinity to infinity, that will not hold more. The reason behind this is that we are using u of tau and u of t minus tau, so we need to find the overlapping region in which the both the function u of t and u of t minus tau is 1, because if either of this function is a 0, then this whole multiplication will be turned to a 0, right? Either u of tau would be a 0 or u of t minus tau would be 0, then all this function will be turned out to 0. So only the portion which is appear is the overlapping region where u of tau is not 0, means u of tau is 1, and then u of t minus tau is also 1, right? So we need to identify this portion where this both are 1. So here we need to understand this thing. Let's say the first we draw the u of tau. So u of tau is understand this is the tau domain. U of tau is the function which is equal to 1 for every tau greater than or equal to 0, and it is 0 when the tau is less than 0. It means in this portion, region number 1, this function doesn't exist. But in region number 2 is a function where their u of tau would be continuously 1, right, for all those value of tau. Now we plot for a u of t minus tau. So for a u of t minus tau is basically what we need to understand here. U of t minus tau is nothing else but it is the u of minus tau, and that signal is delayed by some amount t. This signal is delayed by some amount t, right? U of t minus tau is a u of minus tau. So what is the first we need to plot the u of minus tau? U of minus tau would be looks like this one. This is our u of minus tau, right? It's the opposite of u of tau. So it is 1 for all the values where tau is less than or equal to 0, and it is 0 elsewhere. So it's exactly opposite of u of tau. U of tau is 1 for all those value of tau greater than or equal to 0, and u of minus tau would be 1 for all the value of tau which is less than or equal to 0. So it is totally opposite. But we have to find the u of t minus tau. So t of minus tau is u of minus tau with delay by some amount tau. Sorry, by some amount t. So after some amount t, we are getting the signal u of t minus tau at starting delay by some point. So from 0, this point is shifted to this is the signal of u of t minus tau. Now we are interested to find the region or overlapping region where u of tau is 1 and u of t minus tau is 1. Both should be 1. So you can see in this one, you can see in this picture, u of tau is actually 1 from 0 to tau, and u of t minus tau is 1 from minus infinity to t. So if you find the common area, so the common area is a region number 2, right? Region number 3 is the something which is above t greater than 0. This is the greater than equal to 0. It's region number 3. So in region number 3, u of tau exists, but u of t minus tau doesn't exist. Region number 2, both does exist. Both are 1 in fact. And in region number 1, u of tau is exist, but u of tau doesn't exist, but u of t minus tau is exist. So region number 1, if you multiply u of tau and u of t minus tau would be 0. For region number 3, if you multiply u of tau and u of t minus tau, again it would be a 0. But in region number 2, u of tau and u of t minus tau both are 1. So if you multiply them together, then it will produce a 1. It means that this is the reason, this is the only reason, this region is the only the region from 0 to t where both the signals are have amplitude 1. So this is the common region. So now integration limits are basically change. This integration limits are basically change. In this case, u of tau and u of t minus tau, this integration limit is changed from minus infinity to infinity to 0 to t. Right, this is the reason why these integration limits are not converse for not maybe applicable for minus infinity to infinity, but it is finally applicable from 0 to t, because outside of this region 0 to t, either u of tau would be a 0 or u of t minus tau would be a 0. In both the cases, our final output will produce a 0, so that is not applicable. So what is the applicable region is the from 0 to t. So now in that case, the u of tau is 1, so we can replace with the 1, and u of t minus tau is also 1, so we can replace with the 1, right? So what left with us, e raised to minus 2 times of tau multiply with e raised to minus 4 times of t minus tau. But if we separate this one, it's a e raised to minus 4t and minus minus plus, so e raised to 4 tau. Now this integration is with respect to tau. So the terms which is not related with the terms or which doesn't contain any terms related with the terms, then can be separate out. So we can kick out this terms e raised to minus 4t from this integration, right? Because there doesn't have contains any value of tau, any impact of the variable tau. So if we kick out it from the integrations and kept it out, so we left with the equations e raised to minus 4t and this integration from 0 to t e raised to 2 tau d tau, right? If we take the simple integration and apply the limit, so that e raised to 2 tau, if we take the integration, so it is e raised to 2 tau by 2. It is e raised to 2 tau by 2, and if we apply this limit 0 and t, then it is e raised to 2t minus e raised to 0, right? And if we solve this equation e raised to minus 4t by tau e raised to 2t minus e raised to 0, Then finally, after some calculations that we can comes out to e raised to 2t minus tau and apply e raised to minus 4t inside, so that they turn out with e raised to minus 2t minus e raised to minus 4t by multiply with 1/2 into u of t. U of t is indicating that this signal is basically starting from 0. So here u of t is not present, but to make the understanding to the user, make the understanding of the users that we are multiplying with the u of t. So it indicates that this signal is basically starting from 0. So u of t is internally, externally added over here to make this sure the signal is basically starting from 0. Okay, so this is the final answer, and that way we can solve the some other kind of examples for a convolution. Now we move to the next example, and in next example, uh, yeah. So in the next example, we have been given x1 of t is equal to t time of u of t, and x2 of t is equal to t time of u of t. Now, this most of the subject is basically contain the mathematical part, and whereas less things are related with the theory. Most of the things are basically mathematical. So, and mathematics can be better understood if you do parallelly the things. So whatever I am talking from here, if you simply just listen, then it may not help. What you need to do is that you have to parallelly calculate the example with me, right? Maybe your speed and my speed may not match, but the thing is that if you do the parallelly, so you can get the better idea, and you can get the way how to understand the more better way, right? So it is essential that you can use the note and pen, and rather than can have a passive learning, you can do the active learning and calculate the example with me. Apply your logic and try to solve the example with me, parallelly with me. Yes. So now it's x1 of t is given as a t into u of t, and x2 of t is given as a t into u of t. We need to find the convolution between these two signal. So first we produce x1 of tau. X1 of tau is a tau times of u of tau. X2 of t minus tau. This is the second terms of convolution. That is every t is replaced with the t minus tau. So the equations are t minus tau into u of t minus tau. The terms of u of tau and u of t minus tau is approximately the similar terms what we have discussed earlier in the earlier exam, what we have discussed in the earlier example. So now if you find the convolution between these two signal x1 of tau, x1 of t and x2 of t, so that is integration limited by the lower bound minus infinity and upper bound of infinity. That is x1 of tau into x2 of t minus tau d tau. Now this x1 of tau is replaced with this one, tau times of u of tau. So that is tau times of u of tau, and x2 of t minus tau is replaced with the t minus tau time of u of t minus tau. So we can put this value here. This value is x2 t minus tau, and this value is x1 tau. Right, now we try to solve this one. So this u of tau and u of t minus tau have a common overlapping region start from 0 to t. That part we have already discussed in earlier example, so we are not repeating this the same things over here. But considering the u of tau and u of t minus tau both are 1 within the region of 0 to t, so the limits of minus infinity to infinity can be reduced to the 0 to t, and inside that limit we can have the two signals u of tau and u of t minus tau are 1, so it can be replaced with a 1. So that left with us only the tau multiply with the t minus tau d tau. And if we simplify this, so it is t times of tau minus tau square, and if we take the integration further, so that left with the two separate integration, one for d tau and the second for tau square. And this tau square in integration is t tau q by 3. We can apply the limit 0 to t, and this t tau is actually t is common, so it left with the tau square by 2. We can apply this limit 0 to t. So then it is t square by 2 here, and it is t cube by 3. If we apply this t multiply this, so it is t cube by 2 minus t cube by 3. And if you solve this one, so that left with us 3t cube minus 2t cube divided by 6. So it is t cube by 6 or 1 by 6 t cube, right? So it is t cube by 6 or 1 by 6 t cube, and this limit is h of u of t. U of t is applied over here, right? U of t is the indication that the signal is starting from 0. It is applicable for t t greater than or equal to 0. So this is the second examples that we have solved. We will a couple of more examples we are going to solve today, and from next week that we will see the graphical method. We will again move with the graphical method for some examples, some convolution examples, like as a convolution between two rectangular signals, or convolution between the rectangular and exponential signal, rectangular and triangular signal, etc. So here let's take a look of this third example. We have been given x1 of t is equal to cos of t, multiply with the u of t. X2 of t is simple u of t, right? U of t is a unit step signal. And then here if we produce x1 of tau, so x1 of tau is this one is our x1 of tau, that sorry, yeah, x1 of tau and x2 of t minus tau. This one cos x1 of tau is actually our cos of tau, right? And what is the x2 of t minus tau? So every t is replaced with the t minus tau, so it becomes a u of t minus tau. So that is our x2 of t minus tau. So if you multiply u of tau and u of t minus tau, which are 1 for the limit of 0 to t, so again the integration limits from minus infinity to infinity are changed as a 0 to t. So the term left with us is cos of tau only, and if we take the integration of cos of tau, that becomes a sine of tau, sine tau. And if we apply this integration limit 0 and t, so it is a sine of t minus sine of 0. But the sine of 0 is itself a 0, so it left with the sine of t only. Okay. So the output of this convolution operation x1 of t and x2 of t is equal to the sine of t. So this is the final answer. Now I hope the next example we all will solve together, and that is x1 of t into e raised to minus 3t u of t, and x2 of t into is equal to u of t plus 3, and we need to find the convolution operation between these two signals. So first part is we have to produce a x1 of tau signal. This is the solution. So x1 of tau signal is e raised to minus 3 tau into u of tau. Then the next signal is x2 of t minus tau. So every t is replaced with the t minus tau. So that left with us u of t minus tau plus 3. And this signals u of t minus tau 3. How we can represent? So we can represent as a u of minus tau. Tau is replaced with the minus t plus 3, right? So that can be represented in this form. So it indicate a minus tau. This is, it is delay, right? Minus tau is delayed by some amount, and what amount is a delay by the amount of t plus 3, right? This is very important. Later on we see the significance of this one. So now if you find here the convolution operation between the signal x1 of t and x2 of t, so it is equivalent to the integrations left with minus infinity to infinity x1 of tau into x2 of t minus tau dt d tau, sorry. And x1 of tau we have already found earlier, so that is minus infinity to infinity. X1 of tau is e raised to minus 3 tau into u of tau, multiply with the u of t minus tau plus 3 d tau, right? So the first term e raised to minus 3 tau u of tau, it is our x1 of tau, and the second terms u of t minus tau plus 3, this is our x2 of t minus tau tau. Now we want to change the integration limit from minus infinity to actual limit. So here we need to understand what is the area, what is the area in which u of tau and u of t minus tau plus 3 are 1, both are 1. So first we find the u of tau. So that we know, if we do some exercise over here, so that we know that this function u of tau is would be a 1, it would be a 1 for all these points greater than 0. So u of tau is equal to 1 for when the t is greater than or equal to 0 and is equal to 0 elsewhere. Okay, now the another function with us is u of t minus tau plus 3. So we have already discussed it is actually u of minus tau delay by the some amount t plus 3. So first we need to produce a u of minus tau, and if we produce a u of minus tau, so it looks like the signal, this is the u of minus tau which is 0 and all. So u of minus tau is actually the signal which is opposite to u of tau, and that is 1 for all this value of t less than or equal to 0, and it is 0 elsewhere. So you find the region in which the u of minus tau does exist. Now what we need to find, we need to find the u of minus tau minus t plus 3. It means this signal, the signal is delay, the signal is delay by some amount 0 to t plus 3, right? And then if you plot this signal, so this signal is u of minus tau delay by minus t plus 3. And then after the delay by t plus 3, that how we can represent the signal is a u of minus minus plus and that this signal is u of t, this is t minus tau plus 3. So that is we can say if it is delay by some amount, and after if we producing the signal, so that is a u of sorry, it's a t is also there, so it's a multiply here. So that is becomes a minus tau minus minus plus plus t plus 3, right? So now we will find the overlapping area of this signal. So this signal is actually 0 to t plus 3 is the overlapping area in which this signal does 1, the u of tau is 1, and u of minus tau plus t plus 3, it is also 1 from 0 to t plus 3. So 0 to t plus 3 is the overlapping region in which the both these integration limits are changing from 0 to t plus 3. This is the point where both the signal does exist, and in that case u of tau is 1 and u of t minus tau plus 3 is also 1. So if we replace this, both the terms will be 1, so we'll have with only e raised to minus 3 tau d term, and simply we take the integration of the signal. So the integration of the signal will becomes e raised to minus 3 tau divided by the minus 3, and the limits are applied as 0 to t plus 3, right? And if you solve this one taking the minus 1 by 3 as a common, so that we left with e raised to minus 3 tau is replaced with the t plus 3 as per the integration rule, and the second term is e raised to 0, so that is minus 1 by 3 e raised to minus 3 t plus 3 minus 1, and if we give the sign inside, so that becomes a 1 by 3 1 minus e raised to minus 3 t plus 3. So that is the convolution operation result between x1 of t and x2 of t. Right? So this is the final result of the convolution operation between x1 of t and x2 of t. So now we move to the final example of today, and a few more examples are already given in a book of Anand Kumar, as well as you can even use the second book of Openham, right? So you can go with this book for more examples. In Openham, most of the example given is this unsolved example, but in this book of Anand Kumar, the many examples are given as solved examples. So we take the reference of this and calculate some more example. So we now finally came to the last example for today's session, and then we find the convolution operation between the two signal, which x1 of t is r of t signal, r of t is a ramp signal which can be represented by t. So and the second signal is x2 of t e raised to minus 2t into u of t, right? So here if we can say this two signals does exist, so x1 of t is equal to r of t can be as a t, and x2 of t is simply represented as e raised to minus 2t into u of t. So if you solve this one, so first what we need to find is we have to find x1 of tau. So x1 of tau is tau because every t is replaced with the tau. So this t x1 of tau is equal to t is also replaced with the tau. And if we find x2 of t minus tau, so every t is replaced with the t minus tau, so e raised to minus 2 t is replaced with the t minus tau into u of t minus tau. Okay, okay, so now we are free to convolute this x1 of t signal with x2 of t signal, and that is equivalent to the integration limit from minus infinity to infinity x1 of tau into x2 of t minus tau, and that is equal to t. So if I place x1 of tau is a tau, this is our x1 of tau, and x2 of tau with e raised to minus 2 t minus tau into u of t minus tau, so d tau. So can anybody will let me know what are the limits of this signal, right? What are the limits of the signals? I can replace this one. For the first one is this is our x1 of tau, and the second signal is x2 of t minus tau. So can anybody will let me know what are the limits? I can change the limit from minus infinity to infinity with which limit? So tau is a 0 to t, right? Because why? Because u of t minus tau does exist from 0 to t, so that is the limits are basically changed from 0 to t. Fine. So sorry, I use the blue color pen to make the continuity. 0 to t, and that is the tau e raised to minus 2t. If I expand this equation, so minus 2 multiply with the t, so we have two separate terms are there, 2 tau, and u of t minus tau would be 1 in this region, so it is replaced with 1. So that is the final equation. Now in this one, e raised to minus 2t, I take it's not related with any integration because integration is taken with respect to tau, so I kept it outside of this integration, and the limit is remains with us is tau 0 to t tau into e raised to 2 tau d tau. Okay, now we have to find this integration, but there is some common formula. If you if the common formula will suggest us that is something is in form of integration of x into e raised to ax dx, right? Here we have same things. Rather than x we have a tau, and rather than e raised to x we have a e raised to 2 tau. So if something of integration of x into e raised to ax dx, so that is equivalent to 1 by a square. A is the coefficient of x into e raised to ax in ax minus 1, right? So you can simply integrate, and this is the simplest form. If you do the integration, that you are also getting the same thing. So now what is a in our case? A in our case is the 2, which is multiplied with the tau, and what is the x in our case? That is the tau. So we can apply this formula and directly take the integration. So this is the output of this integration. So as per this formula, we can write 0 to t is the same way, and this one tau into e raised to 2 tau we can integrate like this. So we have a common formula, 1 by a square into e raised to ax minus 1. So a is equal to 2, so we can say it's a 2 square multiply with the e raised to ax. Is a is 2 and x is tau, so e tau, right? We can a is the 2 and x is the tau, so e raised to 2 tau ax again. Ax is again 2 tau minus 1. So this is the simplest way how we can solve this one. Now the limits are still there, 0 to t we can apply this limit. Okay, so first is 1 by 2 square is 1 by 4, so we take it out. So we have a e raised to minus 2t by 4. 2 square is 4, and we apply the limit. So this first we apply the tau is replaced with the upper limit, so it is e raised to 2t. This is also tau is replaced with the t minus 1. We have applied the upper limit. Now we apply the lower limit 0, so e raised to 0, it's a 2 time tau is again replaced with 0 minus 1. So if you solve this, we can have e raised to minus 2t by 4 inside a bracket e raised to 2t minus 1. E raised to 0 is 1 and 2 into 0 is 1, but it's a minus 1 minus minus plus, so we are getting here 1, right? and that is the right answer. But if you want to further simplify this by taking 1 by 4 as a common, and e raised to minus 2t we kept inside, so e raised to minus 2t into e raised to 2t, t2t minus 1 plus e raised to minus 2t, right? We multiply e raised to minus 2t inside a bracket, so e raised to minus 2t and e raised to 2t becomes a 1, so that we're left with 1 by 4, that is 1, so it becomes with the 2t minus 1 plus e raised to minus 2t. That is the final answer, and that is the result of this convolution function. What is the convolution function? Is x1 of t and x2 of t. So this was the final example. If you have any doubt, you can ask me the question. Otherwise, this was the last example. I sign off from here and sign into my desktop PC to take your presence, and where we can have some conversation. If you have any doubt, we can solve that doubt, and otherwise we conclude this session of today. So just wait for. Okay, so just wait for 1 more minute. I just to take in your presence. So have a good day, and have a nice time for all of you. If you have any doubt, you can ask me the question. You can raise your query. Is it audible, right? So you can raise your query if you have any doubt. Otherwise, we can put the session over here.
Thank you, sir.
Okay, so be tuned and solve more examples from the book which is provided to you. And if possible, then you can take a note and pen and prepare a note parallelly to me, right? Okay, so may have a good teaching experience. Okay, have a nice day.
Thank you, sir.
Thank you, sir.